Okay, good afternoon, good evening, and good morning, everyone. Welcome to Thermal Transport Cafe. My name is Yuta Kita. I'm from King's College London, and I'll be chairing today's seminar. So it is my privilege to welcome our speaker today, Dr. Daniel Orejon. Dr. Orejon is a senior lecturer in chemical engineering at the University of Edinburgh. After completing his master's degree at the University of Seville in Spain, he studied his PhD at the University of Edinburgh. And after that, he joined the International Institute for Carbon Neutral Energy Research at Kyushu University in Japan as a postdoctoral researcher. And that's where we met. And later, he became an assistant professor there and then moved back to Edinburgh as a lecturer in 2019. So today, his talk is titled Functional Grafted Surfaces for Wetting and Phase Change, which I believe has something to do with his recent publication in scientific reports, for example. So Dani-san, if you're ready, the floor is yours. Thank you.
Thank you, Kita-san. One sec. All right. Can you confirm whether you can see my screen?
Yes. Yes, we can.
Yeah. All right. Perfect. Thank you, Kita-san, for the introduction. So, and thank you also the organizers. So I wanted to introduce today some of the work of my PhD student, Anna, as Kita-san will introduce on functional surfaces, in this case, silicon oil grafted surfaces, and the potential characterization and applications for phase change, both evaporation as well as condensation. So here is a little bit of my background. I just pass it the different steps that I have done since I started my undergraduate degrees in the University of Seville, as this has been very well introduced by Kita-san, the chairman. So before I start with my presentation, I wanted to basically thank the organizers. And I'm putting this example on the left-hand side, as this is actually the second thermal transport cafe that I acted as a chairman. And this was when the initiative started in December 2020. And we are now February 2024. And finally, I am presenting some work. So actually, Matteo had to come all the way to Edinburgh last May. And although looks like he was presenting some work on boiling, he was actually thinking, Dani, what the hell, when are you going to come to present at the Thermal Transport Cafe? So I just wanted to thank the organizers and also Kita-san standing there in one of the southwest points of Africa when we went for the heat transfer conference in Cape Town. So after this small introduction, I wanted to introduce the topics for today's talk. Hopefully this will be done within 35, 40 minutes, and we will have some time for discussion. So the first of the topics is basically the application and optimization of silicon oil grafting for low hysteresis and low adhesion surfaces. Then we move on to applying these surfaces to droplet evaporation and to see whether we can actually control the different evaporation modes during the phase change of a droplet on a surface. I then move into the opposite phenomena, that of condensation. So instead of the droplets vanishing, the droplets are growing inside in this case. And then if I have the time, I also wanted to introduce a topic maybe not so much related to thermal transport research, but that is intrinsic to most of our jobs as academics, And in this case, I wanted to introduce some work that we have done in innovative learning and teaching related to the chemical engineering laboratories. That is what I mainly the course organizer of, as well as I am the discipline manager here at the School of Engineering for Chemical Engineering. So we start a little bit with motivations. I think some of you may have seen these slides or these snapshots either in this type of presentations or in real life. And basically to point out that drops are everywhere, and they are also related to many different applications, both at the industrial scale as well as in our daily life applications. Example is distillation of whiskey, where we have actually do an evaporation and condensation process. And another example of kind of daily life could be maybe the onsen that Matteo enjoyed last December when he visited Japan. And it was also one of my favorite places actually to observe condensation and evaporation interfacial phenomena. Moving a little bit, so all those applications are kind of very beautiful, but they are unlikely to get funded. And in order to be able to get funding, you really need to put forward some different motivation. In this case, is how we can make use of interfacial phenomena or phase change to be able to, for example, act on the energy flow and mainly try to decrease all the energy that is rejected into the environment. So this is an example of the United Kingdom energy flow, all the energy that is put into the system via fossil fuels, natural gas, or renewable energies here, and the different applications and the different energy used actually and rejected. From this figure, you can see that from, for example, electricity generation, industrial use, and transportation sector, almost 53% of the energy put in the system is rejected as heat. When we look into the state of Texas, is even much higher, up to 65% is actually rejected from just these three sectors. And when we look into US, is even higher. So there is a lot of scope to try to, about all, as you can see here, to try to make use of phase change into electricity generation, for example, to try to increase the energy utilized, so to decrease the energy wasted and CO2 emissions. And some of the applications, as you may know, is for IT data center cooling, air conditioning units, electricity generation, any kind of steam or closed cycle where we have evaporation and condensation. All these kind of fundamental information and fundamentals that we are learning little by little could be potentially utilized to improve some of these applications, as well as water harvesting. And we try also to map our efforts with the United Nations Sustainability Development Goals. In this case, they match pretty well the clean water and the affordable clean energy goals. All right, so once introduced the motivation, I'm gonna go through the different topics. The first one, again, optimization of oil grafted surfaces. And in this case, this slide shows the surface fabrication, how we apply the coating and how we graft and functionalize the coating on the surface. In order to do so, we look at the work of Eifert et al. In the group of Stefan Hart in Germany, that they propose that if we have a clean substrate and we apply the oil and we bake it at 300 degrees, we create a very smooth layer of the silicone oil after cleaning. And then they decided to impregnate again to get the low hysteresis. So in our case, we try to minimize the fabrication steps, and since the idea is to kind of impregnate the coating again, we thought why we are gonna clean and remove the liquid impregnated if just after grafting there might be already some oil remaining on the surface that can act as the kind of lubricant film, giving us low hysteresis surfaces. So basically we skip those steps. The different steps that we did are represented here on the right. So basically we clean with ethanol, acetone, we apply air plasma cleaning. We found that air plasma cleaning is beneficial in two ways. One way is that it removes any volatile organic compound that may attach to the surface. If there is some of these volatile organic compounds attached to the surface, the silicone may not be able to graft or to bond to the surface. And on the other hand, we also found that if when we apply oxygen plasma, the oil spreads much better over the surface, and it also evaporates much nicer and much more homogeneous over the surface. So those were the two reasons, and we were able to skip a couple of steps. In order to characterize the surface, we use a typical drop shape analyzer, custom-built drop shape analyzer, where we have the droplet, a syringe where we put the droplet, and a camera where we are able to basically observe what are the different contact angles upon droplet deposition equilibrium on the original silicone surface, as well as on the oil grafted surface. So after one step, it is clear that we can change the wettability from hydrophilic to hydrophobic. And as you can see here, although there might be some oil remaining on the surface after the grafting procedure, as you can see here from this picture, there is not really an obvious wetting ridge of oil. So we can kind of assume that the amount of oil remaining on the surface is very small and shall affect little the equilibrium contact angle, at least. So in earlier works, like the work from Stefan Hart's group, they only try one single type of oil, for example, and one single type of grafting procedure. However, we thought that viscosity of the oil may play a role, both on the size of the grafting polymers left on the surface, as well as how the contact line recedes during the evaporation and the grafting. And also by trial and error, Anna, she also found that based on how we apply the oil, based on how much oil we deposit by steps, and also on the number of layers, we could actually get different interactions between the droplet and the surface. So we use a similar custom-built setup. And in this case, how we try to understand on the interactions between the droplet and the surface is basically looking at the advancing and receding contact angles. The advancing and receding, advancing in this case, and receding contact angles in this case, give us an idea of the contact angle hysteresis and how a droplet adheres, or how a droplet interacts with a surface. The lower the contact angle hysteresis, ideally the more mobile the droplet is, okay? So we took all the different surfaces that Anna prepared, and we characterized them both in terms of wettability and contact angle hysteresis. When we look into wettability, the different oils that we deposit, 5 centistokes, 20 centistokes, and 100 centistokes. So with this graph here is for 5, 20, and 100 centistokes. In the x-axis, we represent the number of layers, and the different symbols represent different volumes or deep coating parameters. So aside from the deep coating parameters here at 0.2 millimeters per second for 5 centistokes, we can see that almost independently of the volume, of the viscosity of the oil and the volume of oil deposited, as well as the number of layers, all our results on the equilibrium contact angle are self-contained between 104 and 110 degrees. This is kind of the exception. So from here, basically no major differences. We observe a big difference in this case, and we think that in this case, for a 5 centistokes oil, with a very thin layer of oil deposited before grafting, what is happening here is that the amount of oil is not enough, and as the oil evaporates, some part grafts to the surface, but it leaves patches of non-covered regions. And this makes that the droplet will have a equilibrium contact angle in between the bare silicon substrate that is underneath and the wettability of the grafted oil. When we look into the hysteresis, we can see quite big differences. So top figures represent the contact angle hysteresis, defined as advancing minus receding contact angle. And bottom shows the sliding angle, that is basically the angle at which, if we are tilting a surface, the angle at which the droplet will start to slide from the surface. Technically, and as you can see from this figure, contact angle hysteresis and sliding angle should go typically hand by hand qualitatively, okay? Doesn't go quantitatively, but qualitatively. If a surface has high contact angle hysteresis, the sliding angle will also be high, okay? That's why qualitatively you see trends that decrease. For example, for the 10 microliters drop grafted, the trend decrease as well as for the 2 microliters. The same happens for the 20 centistokes oil. I think to highlight is the very low hysteresis of the 2 microliters grafted oil here. And then we have also when we graft 100 centistokes oil, when we use the deep coated method, so we put the sample in a deep coater inside the oil, we lift it, and we leave a layer of around 0.2 micrometers or millimeters of oil on the surface that after we graft. Okay, this one here, the 0.01, sorry, is the velocity of the deep coater. And then we put in the heating plate. And you can see here that one step of 100 centistoke grafted oil is able to give me contact angle hysteresis even below of 0.5 degrees. Let's say contact angle hysteresis of 1 degree or less because of the accuracy of the measurement. So this was very, very exciting finding for us because earlier work reported around 2.5 to 3 degrees of contact angle hysteresis, but after following all the many steps that you saw before. So in our work, by suppressing 2 or 3 of the steps that were proposed before, we are able to halve or even have a contact angle hysteresis that is 3 to 5 times less than what it was originally out there. So this is a little bit of the conclusion from this slide. That is basically 100 centistoke is the best, whereas for 500 centistoke, because again sometimes this oil evaporates, and when it evaporates, leaves many empty regions on the surface without the coating. That's why we are having high hysteresis for the low viscosity oil. So when we look at both of the wetting and contact angle hysteresis results, here we can see that basically when we look at the contact angle hysteresis, the higher viscosity oil, 100 centi-Stokes, I call it high because it's the higher that we are showing here. But when we look into viscosity of oils, I would say that 100 centi-Stokes might be within the medium or even low viscosity regime. But for us, it's the highest. We tried 1,000 centi-Stokes, but the viscosity is so high that affects a lot the evaporation and the grafting process and leaves cracks on the surface, which is not beneficial at all for our purpose. So overall, these, from the parameters that we studied, these are the suggested ones. So if we work with low viscosity oils, we would like to use the pipette method because we are able to deposit higher volumes of oil. These are needed, okay? And also higher number of layers are required as pointed out earlier. Whereas when we go into high viscosity oils, the preferable method is the deep coating. So we leave a thin layer with little volume of oil, and also the lower the number of layers, kind of the better as well. So as you can see here, we were able to enforce a 1 degree of contact angle hysteresis. We were able to decrease 2-fold or even 5-fold the contact angle hysteresis when compared to earlier works. And it looks like when, depending on the fabrication parameters, we can actually tune the contact angle hysteresis. So this last finding is what it prompted us to make use of these surfaces and the different grafting parameters to try to understand better phase change, both during evaporation and during condensation. If you guys want more details here, feel free to contact my student, Anam, not within this week because she's getting married in Pakistan this Saturday, but after that, or myself, or read and have a little look at this published paper. So once we know how we fabricate the surface, we apply these surfaces for droplet evaporation. This was actually a master project from one of our chemical engineering students who spent the first semester doing evaporation experiments on these surfaces. So as you know, when we have evaporation, basically the liquid changes phases from liquid to gas, and when it contains particles, it leaves many different types of shapes, right? That we call the coffee ring effect. This schematic was done by Kita-san, and it kind of shows quite well that although a droplet is a very kind of simple system, there are many intricate mechanisms taking place. And if you want more details on the mechanisms that can take place on these during a droplet evaporating, you can also have a look at the review paper from Sejin Wan. She presented in the Thermal Transport Cafe last year. And you can see all the different mechanisms that play a role on the modeling of a droplet undergoing phase change. And as you guys may know, there are also many other applications in this particular case for droplets and phase change. I put forward before some applications for refrigeration, phase change, but also when it comes to just droplets, there are also many other applications, like, for example, inkjet printing, as we can see here, or for coating of particles, as well as casting or other type of coating with drops. They are also very important in microfluidic applications, and they are also very, very important for biomedical applications where we can carry out DNA tests, for example, or we can understand whether a patient is healthy or not from the shape of the deposit left upon evaporation. So for those of you that might not be very much into this topic, when a droplet is deposited on a surface, depending on the wettability and the surface structure of the surface, in summary, on the physico-chemical properties of the surface, a droplet can evaporate in the CCR mode. This is the constant contact radius mode, and basically the droplet evaporates with a pinned contact line, as you can see here. It's pinned and the contact angle decreases to account for evaporation. If the surface is hydrophobic or it has low contact angle hysteresis, for example, the droplet can evaporate in the CCA mode, constant contact angle mode, where basically the constant angle, the contact angle remains constant and the droplet evaporates with the constant, with the radius receding in time. And we can have also the mixed mode where both the contact angle and the contact radius decrease in time. This is typically observed at the very end of the evaporation, where the droplet becomes quite small. And in the presence of structures, in the presence of particles in the fluid, we can have also the so-called stick-slip mode, where it combines a series of constant contact radius periods with jumps of the contact line. So I would like to introduce first how a droplet typically evaporates on a hydrophilic surface, in this case, silicon. You can see from this figure that droplets typically initially evaporate with a pin contact line, where the contact angle decreases, and then the contact radius decreases with a sort of constant contact angle mode, finishing with a mixed mode where both the contact angle and the contact radius vanish in time, decrease in time. Whereas on a hydrophobic Teflon, as mentioned earlier, a droplet basically evaporates initially with a very, very small thinning of the contact line, but typically most of the evaporation ensues in the constant contact angle. So all this region, the angle is constant, whereas the contact radius decreases until the end, where we have the mixed mode. So we were thinking if our surfaces can be tuned and we can achieve different contact angle hysteresis, then we shall be able actually to control and tune the evaporation of our droplet within these kind of benchmark regimes for hydrophobic and for hydrophilic. So the same fabrication parameter, the same type of surfaces that you see that I presented earlier, viscosity of oil, different volume deposited, different numbers of layers. And here we have made a summary here on the contact angle and the contact angle hysteresis. So basically, if we focus on the contact angle hysteresis and we focus initially on the ones that report very high contact angle hysteresis, you can see that because of the high hysteresis, the experiments are actually not very repeatable. All this shaded area is basically the kind of error or standard deviation upon 3 to 5 repetitions of a droplet evaporating. Whereas the solid lines or the kind of solid dash or dotted lines are basically the average. But here, for the high hysteresis ones, basically we are getting quite a lot of pinning at the beginning and then a receding of the contact line. But again, with quite scattered results. However, when we move into a little bit lower contact angle hysteresis of these surfaces, we can see here that the initial pinning time is quite greatly reduced, right? Here we were reporting between 0.15 and 0.3 of the normalized time, whereas for lower hysteresis ones, we can decrease the pinning time for just the very first 10% of the droplet lifetime. So it's a quite big difference when we are looking that it is the very same type of oil. The only thing that changes here is actually the fabrication procedure. So here, more volume of grafted silicone lowers the pinning. So ideally, we would like to have a pipette rather than deep coating because we are able to put more volume that is beneficial for covering better the surface. And also from the greater number of layers, the better also. So clearly here, if we take into account the green, red, and blue, as we increase the number of layers, this blue layer here, the blue line, shows almost no pinning at all because the number of layers are able to cover the whole substrate and mask the interactions with the silicone. When we move into 20 centistokes of silicone oil, we can see that now most of the behavior, they kind of overlap almost independently of the fabrication parameters. We have a kind of nice constant contact angle for most of the droplet evaporation, except for these ones that they are a little bit of the exception. But you can see here, very low pinning in the beginning, less than 10%, and then all these lines that are almost straight, meaning that there is almost no pinning. Droplets evaporate mainly in the constant contact angle mode. They evaporate similar as on a hydrophobic surface, similar to Teflon. So I think the takeaway point for the 20 centistokes is basically the more volume, better. These kind of not nice results that you can see here, I think they were for the lower volume. And then the greater the number of layers, again, the better performance. And then we move into the 100 centistokes grafted oil. This is the one where we got the best results so far. And as you can see here from the base area or the base radius, there is almost no scattering amongst it. And independently of the number of layers and the volume deposited, for the 100 centistoke, we are always almost getting a very nice receding motion of the contact line while it maintains the nice same contact angle over almost the entire evaporation, except at the end. Okay. Note here that we are almost suppressing 100% the pinning time. Teflon, as you may remember before, it has a small, maybe 4 or 5% of pinning at the beginning, whereas with these surfaces, we are able to fully suppress any pinning of the contact line. So just one deep coating, just one grafted layer, just one step, best performance here. So this figure here is one of the points that I try to convey to you at the beginning of this topic, and is whether we could actually tune our behavior of the droplet evaporation within the Teflon evaporation, that is the red line, and the bare silicone evaporation, that is this black gray line. And as you can see here, most of our results, both in terms of contact angle, both in terms of base area or contact radius of the droplet, all of them, they kind of sit in between the behavior zone for silicone, benchmark hydrophilic surface, and that of Teflon, benchmark hydrophobic surface. So just based on the fabrication parameters, we can be closer to silicone evaporation or closer to Teflon. We also did an analysis on the percentage that these droplets spend on each of the evaporation modes, and the ones for either 20 centistoke with 3 layers or the ones for the 100 centistoke oil with a deep coating deposition, we can see that they suppress the constant contact radius mode. okay? There is no CCR mode present, everything is CCA. Whereas, so very similar also in terms of percentage of duration of the CCA, they are very similar to Teflon, okay? Whereas when we are in using low viscosity oil and when we are applying a very thin layer of the oil with 3 number of layers though, we can actually induce almost 30% of CCR mode at the beginning and around 60% of CCA mode with 10% of the mix mode. So as you can see here, bare silicon and these fabrication parameters, the droplet time in each of these regimes matches quite well. So takeaway points. I just leave them here for you guys to read them while I drink a little bit of water. So I think the main takeaway point from this topic is that based on the different fabrication parameters, we can actually tune our surfaces to induce a behavior similar to that on hydrophilic surfaces or to that on hydrophobic surfaces. So say that, and as most of you know, evaporation, wettability, drop evaporation it was my main work during my PhD. But when I moved to Japan to do my postdoc and assistant professorship there, I actually shifted my efforts towards condensation phenomena. So this is why I also quite like this topic. And based on the findings from the first part, optimization, based on the different contact angle hysteresis that we were getting, as well as on the different results that we got from evaporation, we also thought that the different fabrication parameters must then give us different droplet condensation performance. And this is what we want to demonstrate in this second topic of the talk. Sorry, third topic of the talk. So again, a similar diagram, the way that Kita-san made when he was doing his master's and his PhD. For condensation, as most of you know, wettability, wettability, structural effects, the type of fluid, as well as non-condensable gases are some of the factors that affect the type of condensation that we are going to have on the surface, right? Typically, hydrophilic surfaces lead, or superhydrophilic lead to so-called film-wise condensation, whereas hydrophobic or superhydrophobic leads to drop-wise condensation. And the same can happen with the structures. We can tune the size and aspect ratio or spacing between the structures to induce different wetting regimes as well. As we also know, the type of fluid, higher surface tension fluids tend to form nicer, rounder droplets, whereas low surface tension fluids typically wet more, giving film-wise condensation as the final mechanism. And non-condensable gases, I don't think they affect much the shape geometry, but it will affect the dynamics of both nucleation as well as droplet growth. So when we are in the hydrophilic regime, as mentioned earlier, we get film-wise condensation, hydrophobic regime, drop-wise, and superhydrophobic with structures, we have even droplet jumping. So in order to be able to do these experiments, Anam designed this condensation experimental setup that consists of an enclosure to be able to keep humidity and temperature control throughout, as well as a Peltier state that is connected to a cooling bath. And this is a sort of picture of the setup. As you can see, it's not vacuum closed, so we are doing just experiments using humid air. And we have a couple of cameras, one normal camera to visualize the whole experiment, and a CCD camera, a magnification lens with a CCD camera to be able to get closer snapshots. So on the left, you can see the typical behavior of condensation on our 5 centistoke silicone oil. You can see some drops, big drops at the top, probably because of the edge effect. And we can see how condensation, nucleation happens, then droplets coalesce, they keep growing until they are big enough, like that one there on the side, and they fall from the surface. And on the 100 centistoke, we get a very similar behavior in terms of nucleation, growth, coalescence, keep growing of the droplets. But you may notice here on this side that the size of these droplets that are already kind of going down the surface, the size of those droplets are actually much smaller than the ones that we have on the left. In order to demonstrate that, Anna took different snapshots and analyzed the droplet number density, as most of us have done in the past, like Patty, like myself, to try to basically understand how the droplet population changes in time, or how the droplet population may affect later on the heat transfer across the surface. We haven't moved yet into applying the heat transfer resistance-based model, but we did do this drop number density. Well, Anam did, not myself. Anam did all this analysis of many droplets, many different frames. And I think the takeaway point here is that on our 5 centistokes, at certain intervals of time, we have drops as big as 400 micrometers. That's the kind of maximum radius of the droplets that we can see. Whereas in the case of the 100 centistoke oil, no droplets bigger than 200 or 300. I would say this is 300, sorry. 1, 2, 3, 4, 5, whereas for the droplet number density on the left is 500. So 500 and 300 micrometers. So we are almost able to halve the droplets, the maximum droplets seen on our surface for the different intervals of time observed. So these are the conclusions for this topic. Basically, we managed to build an environmental chamber for this experiment because we were able to apply the different functionalization procedure. We were able to impose different contact angle hysteresis to the surface. That in turn led us to a different droplet size distribution and to halve the droplet departure size. And this work is actually been helpful to us, and we started a collaboration with Rice University following a collaborative scheme between the University of Edinburgh and Rice University. So we are working with Gia Wedmeyer and Daniel Preston, that some of you or most of you know. I think Dan gave a talk few thermal transport cafe ago. And also his Geoff's student, Trevor, who has been also great in collaborating in this project. It's 4:45. Unfortunately, I will not have much time to continue with the presentation. I think related to this presentation, wetting and evaporation and condensation on functional surfaces, I think I have presented and is a good, nice and self-contained presentation. Unfortunately, I will not have time to go in details with our innovation in learning and teaching, but I just wanted to briefly explain what is this topic about. And it's basically myself as course organizer of the teaching labs. Because of the pandemic, we created a lot of material online that we have now applied for our students to be able to prepare before coming to the lab. So we are using different digital tools like Camtasia, quizzes embedded in our learning system, as well as the different learning environment. So we have videos with quizzes that give feedback straight away, different quizzes as well for the students to fill up the blanks, to mix and match as well. They need to do schematics, they need to submit risk assessment. Risk assessment is actually an Kakenhi institution of chemical engineering requirement. So they have a nice 1 or 2 hours online preparation towards the lab, and I think this is the main takeaway point. Most of this work was done by one of our chemical engineering undergraduate students, Hannah Linden. But basically, the takeaway point is that our students consider that this online preparation that we have created, coupled with the manual, give them 90% satisfaction on securing fundamentals, practice, as well as confidence before coming into the lab. Confidence is actually one of the things that our students lack when they leave at the university, when they go into industry. And we think that this kind of online preparation will be very, very beneficial to them. And it's been demonstrated by the kind of responses that we got from the students. So I just wanted basically to move into the overall conclusions. That is, we demonstrated the one-step slippery grafted surfaces and tunable contact angle hysteresis. We were able to tune the evaporation of the droplets, as well as to control the different evaporation modes. We were also able to tune and modify the different droplet size distribution on the same surface, just with a different coating procedure. And we were able to enhance our students' fundamental practice and confidence prior to coming into the lab and do the actual practical work. Before I finish, just to basically acknowledge the University of Edinburgh, ThermaSmart Initiative, our institute, the Royal Society, European Space Agency, Cultural Attaché from Oman, the Higher Education Commission of Pakistan, as ANAM is funded by the HEC, and of course, the supervision team, as well as the students, Astrid, Anam, and Hannah, that, as we all know, they are the ones that they are doing actually the heavy lifting here, whereas we are just here to kind of benefit from their very, very hard work. So I just leave the slide with the conclusions, and any questions either in the chat or in person or via video are more than welcome. Thank you, everybody.
Thank you, Dani-san, for the nice informative presentation covering from topics from surface fabrication and the tuning of the wetting to the applications in phase change. So we have a few minutes for Q&A sessions. If you have any questions, please do speak or type the question in the chat.
Can I ask a question?
Yes, please go ahead.
Please.
Thank you. Very interesting talk. I was curious about your surface, compared to liquid infused surfaces, because they look very similar. So I was wondering, what are the pros and cons compared to that? And second question is, you mentioned for low viscosity oil, it's kind of preferred to have many layers, but for high viscosity, it's the other way around. So it seems like the result indicates that overall, the final oil thickness is actually the key parameter that accounts for both viscosity and the number of layers, I guess. Could you add some comments on that as well?
All right. Very good questions, John. So you are right. These surfaces, so grafting an oil on a surface, not so sure. They are typically called quasi-liquid surfaces. So basically what is happening is that there is the oil chain, they kind of attaches to the surface, but these oils, they have different lengths, right? And the kind of top of the chain is kind of free to move, right? So that's kind of what gives some of the properties. Those will be the properties if we were to later on remove as well the oil. So will just be the chain, okay? So this one specifically, I will say that you can call them maybe quasi-liquid surfaces, quasi-liquid infused surfaces, right? Because you basically have the quasi-liquid state as well as some oil remaining because we did not clean them. But basically, you know, to make liquid infused surfaces, you need many steps, right? Typically, you need structuring, micro nanostructuring, you need coating sometimes, then you need to infuse the liquid, right? So at least 3 types of steps that we are trying to kind of avoid within this work. All right. And regarding your point on the different viscosity of the oil, yes, so in the case of the 100 centistoves, the layer of the grafted chains, they are a little bit longer. So that means that, as you mentioned, they can retain better the oil and they can give a better mobility of the droplets, okay? But I don't think is the case of the 5 centistoves. I don't think that is the thickness of the oil left what is making the droplets to attach, okay? What we saw is that in the 5 centistoke Abotor, when you use very little volume, and because we are using very high temperatures, what is happening is that the oil is migrating from the surface and evaporating and is leaving empty regions, patches of empty regions that we were able to kind of observe also almost with the naked eye. So that's the reason for the 5 centistokes. Does it answer your question, John?
Yeah, kind of, but I'll email you for more detailed questions later.
Sure. Thank you. So I think Mark and Mateo had their hands up.
Yeah.
Mark,
hey, Dani, thanks for the very interesting and thorough talk. I think you partially just answered my question about,
right.
I was going to ask about the durability of the surfaces of the high viscosity versus the low viscosity fluids.
Mm-hmm. So yeah, a little bit more on the durability, Mark. Here, we in the paper that Anam published in the first one, we did a little bit of more thorough stability analysis. So we subjected the surfaces to mechanical vibration. We subjected the surfaces to, we dip them in some solvents. We also did steam condensation. When we did them in the solvents, we were able actually to remove the excess of oil. So we were testing the surfaces and getting the same, even better results than previously the group from Stefan Hart got. Under steam condensation, though, they were not very, I think the conditions there were very hard, but these surfaces have been reported for condensation of low surface tension fluid, that this is kind of one of our next step to try to apply, instead of condensation of water, to try to do organic fluids and refrigerants that are more interesting for you and for the refrigeration community. Thanks, Mark.
Thanks.
All right. Matteo?
Dani, thank you very much. I think this is the time I've received most citations in one day. I actually have a problem, a question, not a problem on the...
Can be a problem too.
The temporal aspects of this process, the evaporation of the droplet, to be clear. You report data in non-dimensional time, and understand you normalize by the time evaporation is
That is right. Yes. Yes.
So
good catch.
I wonder whether, what are the heat transfer nuisances that we need to know about this to make an assessment on which one is the best actually in removing heat and enhancing the heat transfer coefficient.
All right. Good question, Matteo. I think here, so for example, the same as when we do in condensation and we try to do this sort of heat transfer resistance model, right? Basically how heat is removed from a surface or even from the environment by the droplet evaporation is gonna be proportional to the contact area, for example, right? And of course, to the evaporation rate. And in isothermal conditions, what you would like to have, what works the best, basically, is just your hydrophilic surface, because it kind of spreads the droplet the most, right? So you get the most contact area of the droplet with the surface, and also evaporation of the droplets. It is not shown here, but yes, because the normalized time, as you pointed out, but evaporation of droplets are typically proportional to the base diameter. At least when they are in the order from 100 degrees to 0 degrees, they are typically proportional to the base area. Hence, greater base area, greater base diameter, droplet is going to evaporate faster and it's going to remove more heat from your surface. So that will be your hydrophilic. Not here, but just for you, for some kind of ballpoint numbers, 3 microliters droplet, the ones done here for silicon, it will take maybe between around 30 minutes. Whereas on the hydrophobic surface, the very same volume evaporates in 45. So it's almost a 50% longer time for the evaporation on the hydrophobic surface than on the hydrophilic. Again, because the droplet needs to remove heat from somewhere. And if the droplet is hydrophobic, it has a very small area to remove heat from the surface and from the ambient because of the low thermal conductivity of air. Typically, droplets get the least energy to evaporate from the ambient. But this is something that we want to investigate more. I think it's very important to try to couple all heat transfer mechanisms. With NENAD, we did one work where we are looking at the temperature profile around the droplet, not on the droplet itself, around, so in the gas phase. We have another project that I have a master's student now working on that is basically to understand how heat is removed from the surface. And we are trying to then couple ambient, surface, or everything experimental, because you may know that numerically there are quite few works out there where they look into the substrate conductivity or to the ambient, how heat is transferred, but there has been very little work done to this extent experimentally. So we are trying to couple all this.
Thank you, Dani.
You're welcome, Matteo.
All right. There's a question in the chat box, if you can see it, Dani-san. So the question is, you have reported stick slip motion on low hysteresis homogeneous surfaces, and how would you explain this observation?
Very good question, Maya, and yeah, you have really look at the paper. So as I didn't include this part on the talk because would have made this topic just a little bit heavy on the evaporation, but some of you may have noticed that in some cases the constant contact angle mode that I am sort of reporting here is not 100% constant. And what you see here in some occasions is basically what Maya is saying in the chat. You see some distinctive stick slip. So at the end of the day, the droplet contact angle oscillates within the same contact angle, but it does it in what I introduced earlier as the stick-slip mode. So the contact line pins a little bit, and then to account for evaporation, the contact angle decreases, but the hysteresis of the surface is so low that the pinning of the contact line is not maintained and the droplet can depin. And it has these different finite, small jumps of the contact line that if we look at this figure, they are almost non-appreciable. But when we look into the detail, they actually are. And those sticker slip and analysis on the sticker slip, as well as the force balance due to those small jumps, is actually included in the paper. And this sticker slip basically occurs because of surface heterogeneities. So basically the coating or the kind of polymer chain, they are not 100% homogeneously deposited on the surface. About all the short ones, there might be some distance and spacing between the chains that are deposited and between the oil that is impregnated. And this is what causes the droplet maybe to sink a little bit more in some parts, depending on the fabrication parameter, what makes the contact line to pin a little bit more or a little bit less. Typically, the similar findings that have been reported related to suppressing the constant contact radius mode can sort of be applied to or are in line to suppress the stick-slip mode. So basically, the more homogeneous you have the surface and the more linear you have your CCA mode, the least stick-slip you have. And this typically happens. The best, it was for our 100 centi-stoke oil. Very nice question, Maya.
All right, thank you, Dani-san. Another hand, Patrick.
Hi, Dani. Really nice talk there. Just a quick question on the droplet evaporation plots that Matteo was asking about there. I was just wondering what temperature these experiments were run at, because that will affect whether the evaporation becomes dominated by heat transfer from the surface or if it's just mass transfer to the surroundings. And kind of if these were run at room temperature, maybe some investigations on the effect of substrate temperature might be an interesting line of investigation to take.
Very nice hearing from you, Patrick. I hope everything is good at Durham with you.
That's going well.
Thank you for following up on Mateo's and regarding the temperature. As you mentioned yourself, yes, all these experiments were done in laboratory ambient conditions, in sort of isothermal conditions. So 20 to 24 degrees of ambient temperature, humidity is between 40 and 60. Not very well controlled conditions because these were done actually in the teaching lab, as I mentioned earlier, via a master student, Astrid, that was acknowledged after. And I do definitely agree, Patrick, that applying temperature either on the environment or on the surface can be very, very interesting for droplet evaporation. I think for this specific topic, though, maybe we will need a little bit more of control experiments, because when we change the temperature, we will not just be changing the temperature of the surface or of a solid, right? If we were to have copper or aluminum, or maybe some aluminum with one layer of SAM, self-assembled monolayer, right? Where we can consider that the temperature of the substrate is uniform. In this case, because we have the grafted oil also on the surface and maybe some further oil impregnating it, the change in substrate temperature and ambient temperature might change the mobility of the chains, might change also the viscosity of the oil impregnated. And if the temperature is very high, we might even induce without wanting. We might even induce the preferential migration of the oil impregnated towards some regions of the surface. So I think very interesting topic, very interesting thing that we could do, Patrick, but we will need to have very well controlled conditions and understand very well the substrate and the grafting, the oil grafted before moving probably into the droplet.
Okay. Thanks very much, Dani.
Thanks, Patrick.
All right. Is there any other questions? I guess the time is almost running out. I have one quick question, if I may ask. So I'm not sure if you have reported the roughness of all the substrates you tested. You compared silicon wafer, I suppose that is very smooth. And Teflon, I'm not sure the roughness, but I don't know how much, let's say if you have a rough surface, and if you have oil grafted on the surface, how much will this oil grafting affect on the rough surface?
All right. So you are going one step ahead, Kita-san. That's a very good question, right? So we also would like to investigate roughness and the application of the coating, right? Because if we control well the roughness, we might be able to induce Cassie-Baxter state, or as Simon Dye reported, maybe a sort of a slippery Wenzel mold, right, for our droplets. So first, we have characterized our surfaces, okay, and you can see them in this slide here. So the roughness of silicon is actually, can you see the slide? So the roughness of silicon is actually the smoothest one, even smoother than our Teflon. Teflon basically is a silicon with a layer of Teflon anneal on the surface. So any kind of anneal layer on top of the silicon probably will create additional roughness, right? Yeah. Despite the lower roughness of silicon, is the wettability what dictates whether the initial behavior is going to be CCR or CCA, right? Or the kind of main behavior of evaporation. Then for the coatings, Kita-san, you can have a look at the ones here. And this is just for 100 centiestokes. And we cannot tell much, basically, from the profiles and also the increase. I am not 100% positive that these results of the roughness are actually very, very accurate. Because again, we are trying to do, these were done by contact measurements, so not AFM. They were done by DACTAC. And because the surface is kind of quasi-liquid, it might be that the DACTAC, the tip, can affect and can maybe bring some of the coating with it. We did do AFM because we thought it was going to be a much better metric. And we did found a little bit of differences when we compare the different samples. We just did on one layer, 5 centiestokes, 5 layers, 5 centistoke oil, and on the 100 centiestokes, 1 layer and 3 layers. And we also measure the thickness. So yeah, you get some roughness just because of the coating. In this case, where I mentioned that 1 layer might have a lot of patches, is actually the one that probably measures a little bit of the silicone and then jumps into the different polymer chains. So this is why it gets very high kind of roughness there. And I mentioned to you before, so I had my 3 PhD students, actually, they went in August to Cape Town. I don't know if you remember, you meet them for the ThermaSmart workshop. They started there with Marilis, a project where they were using actually the copper surfaces that Marilis is working with. And these copper surfaces, they were both smooth and they had different procedures to induce roughness. One was to make sort of concentric type of rings, and the other one just by sanding. And we just did some preliminary results there, but they are quite promising in terms of that depending on the roughness process applied, whether we are creating higher or smaller roughness, we can actually induce and play with the kind of length and the kind of magnitude of the stick slip behavior of the droplets that Magia was mentioning there. So we are actually looking into that, trying to couple the structures and our coating procedure. Though, just to say, Kita-san, the coating procedure and having a very nice homogeneous coating of these PDMS brushes rely a lot on having a very smooth, uniform surface where your oil will spread very well and where you don't get preferential pinning of the contact line while the oil evaporates and deposits. And all these things, they are kind of what is happening when you have a rough surface, right? So yeah, it can be applied, but we need to do things step by step and very, very carefully.
Okay, that's very clear. Thank you.
Thank you, Kita-san.
If there's no any other questions, I'd like to close this seminar. So thank you for all attending, and I don't know if there is any announcement from Matthew.
No major announcement. Yeah, thanks so much, Dani and Taku, for the great seminar. We'll have another TTC very soon, sometime mid-March, something like that. I'll send you a calendar invite and everything like that as usual. So yeah, thank you.
All right, thank you. So I'll see you soon then. All right.
Thank you, organizers. Thank you, Yanis, for the clapping. Thank you, Maya.
Thank you. Bye.
Bye, all. Have a nice rest of the week.